We are thundering rapidly to the midpoint of the term. I think a week from this coming Thursday will be exactly halfway. And the halfway point is when I usually try, give or take a day, to change gears very abruptly and start looking at the symmetry of physical properties and tensors, an actual discussion of physical properties that are anisotropic. So we'll be finishing up our discussion of symmetry fairly quickly. We still have, however, some major derivations to perform, and we'll get into one of these today. Last time, we had begun the process of deriving what are called the point groups, as opposed to the plane groups. The plane groups were combinations of symmetry with lattice that extended throughout a plane in space. A point group we've seen in the form of two-dimensional point groups. We're now going to today derive the three-dimensional point groups. And again, the name stems from the fact that these are clusters of symmetry about a common point, so that at very least that one point in space stays put. Okay, so hence point groups. These are symmetries about a point. And to put some embellishing adjectives on here, these will be the three-dimensional crystallographic point groups. Because there are an infinite number of point groups, we are considering just those symmetries that can be combined with a lattice and therefore are permissible to crystals. I'd like to point out, in case you've not been making much use of Berger's book, that we actually are getting back to Berger's treatment. We'll do some of the derivations over the next few days with a little bit more detail and with a slightly different procedure than Berger, but the bases covered are the same. So let me just point out where some of this material is in Berger's book. Berger does Euler's construction. And he does this in a once-over lightly. I think this is not the best part of the book. This is on pages 35 to 43. In particular, he sort of leaps ahead quickly and just looks for one angle between rotation axes and doesn't get specifically the ones that are 90 degrees and are not as interesting. Some of the combination theorems are in Chapter 6. And there you'll find the statement that two reflections at an angle mu is equivalent to a net rotation of a 2 mu. Except Berger doesn't call them sigmas, he calls them m's. He uses the same symbol for individual operations and for the symmetry element, and I think that's a little untidy. Also, the theorem that says that if we have a mirror plane that's perpendicular to a two-fold rotation axis, that gives rise to an inversion center at the point of intersection. And then he launches into a rather condensed version of the derivation of the point groups on pages 59 to 68. And then in Chapter 7, derives the two-dimensional lattices, or the plane nets. This is on page 69 to 83. We've done that differently and much more exhaustively by deriving the two-dimensional plane groups. And the lattices are part of the plane groups, and we've gotten them automatically. There is a place where, in the derivation of the space lattices, he's a little bit incomplete and actually does something that's wrong. Aha, I showed Berger was wrong at one place in his book. But anyway, this is where the material that we're covering now is mentioned in Berger's book. Last time, we had hit a new surprise. We had asked if we take the basic rotational symmetries and add an inversion to something like 3. So 3 is a subgroup. The operation of inversion is an extender. we found that there was a new operation that came up, and this was a Roto Inversion operation. And in the resulting point group, which we called 3 bar, the symbol itself, 3 bar, is a threefold Roto inversion. And if we were not clever enough to invent a Roto inversion operation, we would have stumbled headlong over it in adding inversion as an extender to a threefold axis. And a Roto inversion axis is something that involves, in general, rotating through some angle alpha to get from a first object to a second object of the same handedness, and then not yet putting it down, first inverting it through an axis, through a point on the axis to get really a second object. I shouldn't call this second because this is not rotation with inversion simultaneously, but a two-step operation. So we rotate from one to this virtual object, also of same handedness, and then before putting it down, we invert it to get number 2, which is left-handed, and the operation of getting there in 2 steps, but in 1 repetition, is the operation of Roto inversion. That operation was one of the members of the group that results when you add inversion as an extender to 3, but really this was not something that was a new sort of symmetry element. It was an operation that came up, but we could regard the point group that we've labeled 3 bar as simply a threefold axis with an inversion center sitting on it. But then we looked at another one, and by anticipation I said we ought to look at these, and we looked at what happened when we took a 4-fold Roto inversion operation, where we would take a first object, number 1, rotate it through 90 degrees, not yet put it down. We'd first invert it through a point on an axis, and we got one that was 90 degrees away, but pointing down and of opposite handedness. If we repeated that operation several times, we found that we got 2 objects up above a plane normal to the rotation part of the operation and passing through the point which we inverted. So there's one right-handed one up here, a second right-handed one up here, and then 2 down below which were of opposite chirality, number 3 and 4. And that is an entirely new beast. We have no way of describing the relation between these 4 objects other than saying rotate, don't put it down, first invert. Rotate, don't put it down, first invert again. So this is something entirely new. It's a 2-step operation. You cannot describe it any more simply than saying take 2 steps to do the repetition, in the same sense that the glide plane that we discovered in the plane groups had a step of translation followed immediately by reflection, and that was a new sort of operation. So here's another example of a 2-step operation. The symbol for this point group is 4 bar, and the symbol for it, if you want to indicate its locus, is it's got a squareness to it because these objects azimuthally are separated by 90 degrees, but it really has only a 2-fold symmetry. So the symmetry for a 4 bar axis, it's not really an axis at all, it's a 4 bar point because only a point is left invariant. But the symbol for 4 bar quotation marks axis is this square with a little 2-fold axis inscribed in it. All right, we ought to really then step back and ask how many different Roto inversion axes there might be, and add these to our bags of tricks. And what I'm going to invite you to do is to examine this systematically on a problem set, which I will pass around, along with several other problems for your consideration as well. And having stumbled onto that combination, another thing we might ask to broaden our bag of tricks still further is to say, is there such a thing as a rotoreflection axis? And we called n bar a roto inversion. A roto reflection axis is indicated by an n with this little squiggle on top. Anyone who has studied Spanish realizes that the proper name for the squiggle is a tilde, T-I-L-D-E. And this would be an operation where there's a locus in which we'll perform the reflection part of the operation. So this would be a two-step operation that involves taking a first one, rotating it to a virtual object number 2, but not putting it down. Before putting it down, we will reflect in a planar locus. So this is number 2, and it will be of opposite chirality. So that's another operation that involves rotation coupled as one part of a step that involves the second of our 3 translation-free operations, namely reflection and inversion. So are these something we should consider? So what I've invited you to do is to draw out for n equals 1 to 8 the patterns produced by roto inversion and the patterns created by roto reflection, and then see if you regard these as new operations or whether they can be broken down into the simultaneous presence of more than one of our old friends, such as 3 bar being a plain old threefold axis with an inversion center sitting on it. The fact that I'm asking you to take your time to do this suggests that, yes, you are going to find some roto inversion and roto reflection axes which are inherently two-step operations and can't be decomposed. All right, what I'd like to do now then is to systematically look at the axial combinations. And these are of the form n, 1, 2, 3, 4, and 6. And the dihedral symmetries, these are of the form n, 2, 2, or just 3, 2 in the case of the one with the threefold axis. And then the 2 cubic arrangements, 2, 3, two-fold axis out of the face normal to a cube, threefold axes out of all of the body diagonals, and 4, 3, 2. And what I'm going to do with you is to use these as worksheets to guide the logic of what we're doing. And we won't do every single one of them. I think once we do a few, the general principle is clear and the results there are before you. But what we'll take then is the axes n, the axes n, 2, 2, and then the 2 cubic symmetries, 2, 3, and 4, 3, 2. And then finally, we found 4 bar as a different rotation axis-like symmetry element, so I'll add that to the list. And then consider what we can add to these symmetries as extenders. And these are an additional element that we can add to what is already a self-contained nice little group. And we muck things up by introducing another operation. And then we'll have to take combinations of that operation with all the symmetry elements that are there in the parent subgroup and see what new symmetry elements arise. The ground rules in these additions are fairly simple, but nevertheless profound. The addition of the extender cannot create any new symmetry axes by its operation. And the reason for that should be quite clear. We obtained these combinations of rotation axes using Euler's principle. And that was thorough and orderly, systematic, and complete. These are the only arrangements of crystallographic rotation axes that are possible. So if we add an extender that creates, for example, a new two-fold axis in N22, it's either going to be something that we already have in this list and therefore not interesting, or something that just cannot constitute a group. We'll take combinations of operations and we will never find a closed finite set. Okay? So if we add a mirror operation, a reflection operation as an extender, the addition of the reflection operation sigma must be either perpendicular to the axis, and what that's going to do is just flip the top part of the rotation axis and reflect it down to the bottom axis. Nothing new is created. And it could be, alternatively be parallel to the axis and passing through it. In that case, we've already seen the consequences of this addition in deriving the two-dimensional point groups, namely 2mm, 3m, 4mm, 6mm. No new axis is created. One of the additions that is something we mentioned last time is that in the case of the dihedral groups, where we have an n-fold axis and then two-fold axes arranged in some fashion, not in some arbitrary fashion, it's going to be 2 pi over n times 1/2, depending on the n-fold axis. We could pass the mirror operation through the two-fold axis, and that's what we'll call a vertical mirror plane. But when there's more than one axis present, we could also put the reflection operation diagonally in between the two-fold axes. So we're going to refer to this as a diagonal mirror. It's snaked in between the axes that are present. So perpendicular reflection operation as an extender, one parallel to the axis and passing through it, or one that is diagonal, passing in between them. And finally, that exhausts what we can do with reflection, but we could add inversion. And if we're not going to create new axes, and we're going to get a point group, a finite set of objects, the inversion center has to be on one of the single axes, namely these groups N, or at the point of intersection if there's more than one. So there's the job laid out for us. And we've got two theorems to aid us in quickly finding the new operations that arise, in effect taking a shortcut to establish the group multiplication table. And the two theorems are as follows. We saw that if you take a rotation operation a pi, that takes a first object that's right-handed and rotates it to a second object that is also right-handed, and then follow that by reflection in a mirror plane that is perpendicular to the axis, the net effect of going from 1 to number 3, which is left-handed, is to create an inversion center at the point of intersection. So there's a theorem that we can write down once and for all and say that a pi followed by reflection in a mirror plane that's perpendicular to axis A has as a net effect the operation of inversion. And if this is not a two-fold axis, it's something like a four-fold axis or a six-fold axis, that contains the operation a pi as part of the operations contained in that axis, and that's going to create an inversion center as well. So for any even-fold axis, add a perpendicular mirror plane, and automatically the inversion center comes up. And we can permute the order of these operations. If we rotate by 180 degrees and then invert, the net effect is reflection in the perpendicular mirror plane. So this is something that you can permute around into 3 different combinations. Does the order of the operation make a difference? And the answer is no, the order is not important. For example, rotating and then reflecting is the same as reflecting and then rotating. You end up at the same point, number 3. Remember a fancy word for this when we defined what's meant by a group, that these groups are going to be what's called abelian. And an abelian group is where any combination of operations A followed by B is identical to B followed by A. I told you of that great joke among mathematicians, what is purple and commutes? And the answer is an abelian grape. I think that's stupid, but drives mathematicians into guffaws of laughter. A second theorem, this is one that we've already seen in 2 dimensions, is that if you take an operation, A alpha, pass a reflection operation sigma 1 through it, that the effect of that is going to be another mirror plane that is alpha over 2 away from the first. Notice I'm a little bit sloppy in talking about reflection operation and mirror plane, because if a reflection operation is there, that's all I need to have to say that this is the locus of a symmetry plane, a mirror plane. Okay, so this is another one. Do you think that this is an abelian combination? To say that A alpha followed by sigma 1 is equal to sigma 2. Is this abelian? No, it's not. And how do you answer that? Not through any means more profound than just drawing it out and seeing what you get. And let's take 3m as an example. So let's do the operation in this order. Do the rotation A 2 pi over 3 to go from this one up to this one. And then let's reflect across this horizontal mirror plane. So this is 1 right-handed, this is 2 right-handed, reflect. Here's number 3, and it's left-handed. So that's A 2 pi over 3 followed by reflection in sigma 1. And if we do the operations in reverse order, reflect in sigma 1 to go up to here. So this would be 2 prime. And then rotate by 120 degrees, and we would go to here to here. And that is not the same location as this one. So this is not equal to sigma 1 followed by A 2 pi over 3. How can you tell when is the combination of operations going to be abelian and when is it not? It sounds rather clumsy to state it in words, but whenever the 2 symmetry operations leave each other unmoved, then you can permute the order. For example, in this combination here, the rotation leaves the mirror plane unchanged. It just spins it around in its own plane. The mirror plane leaves the rotation unchanged. It just reflects it end to end. Here, this rotation axis and these mirror planes obviously do not leave each other unchanged because the threefold axis rotates the mirror plane to 2 other new locations. So whenever that's the case, if the operations do not leave each other unchanged, the order makes a difference. So that's a useful thing to keep in mind. All right, let's now turn to these sheets that I passed out. And you might want to unstaple them because they're designed to go side by side. And they're 3 pages. And what I've done across the top of the pages is to give the different combinations of crystallographic rotation axes that are possible. So going from the first sheet across to the last, there's the rotation axes by themselves, 1, 2, 3, 4, and 6. Then there are the groups of the form N2, 2, 2, 2, 2, 3, 2, 4, 2, 2, 6, 2, 2, and then the 2 cubic combinations, 2, 3, and 4, 3, 2. So there are the 11 possible combination of crystallographic rotation axes. Stuck off by itself at the end is the oddball 4 bar. Okay, for the axes by themselves, the diagonal mirror addition is not defined. The diagonal mirror position by definition snakes in between axes that are there in the axial combination. If there's only one axis, that's not defined. But you could add a horizontal mirror plane. Horizontal mirror plane added to a one-fold axis is just a mirror plane. So that's called M in the international notation for mirror. And it's called C sub S. C because it's a cyclic group, and the S stands for Spiegel. And that's the Schoenflies notation. If we take 2 and add a horizontal mirror plane, this is the thing that we sketched out here. This gives a pattern of 4 objects, 2 that are up above the mirror plane of one chirality, 2 down below the mirror plane of opposite chirality. These projections of the patterns are down along the rotation axis, and when you see a dot in a circle, the circle represents the point that is down, and the dot is one that's up on top. So there are 2 pairs of objects, 2 right-handed ones, say, that are up, and 2 left-handed ones that are down. And that in international notation is 2 over m. The twofold axis is over a mirror plane, so that's the way to make sense of the symbol and remember what it means. In the Schoenflies notation, it's C2, and you've added a horizontal mirror plane as an extender. Going down the remaining ones in that list, because they're all very, very similar, add a mirror plane to a threefold axis. The triangle is reflected down to a triangle of motifs of opposite chirality. So that's 3 over m. For short, it's called 6 bar, but let's forget about that. The Schoenflies notation, C3h. And similarly, there's a 4 over m, a square above, a square of opposite handedness below the mirror plane. The horizontal mirror plane in all of these cases is shown as a bold line. They've added fainter vertical lines to give you an angular reference. Don't be confused by that. In the Xerox copy, the weight of the lines is not distinguished. So the only symmetry element in 4 over m, for example, should be shown by this solid, bold circle that is in the plane of the paper. The 2 crossed lines are lighter, and those are just azimuthal orientations. Then finally, there's another one of this form, which is 6 over m. And all of the even fold additions, that is to say everything but 3m, if you add that horizontal mirror plane, it's going to be perpendicular to an operation a pi. Therefore, inversion pops up as one of the operations in a group. And 2 over m, 4 over m, 6 over m, those regular polyhedra of objects can be inverted through the point of intersection of the axis and the mirror plane, and that leaves the set unchanged. So if we go down to the bottom of the list and say, can we add inversion to these axial arrangements? In the case of 2, 4, and 6, no, adding inversion doesn't give you anything new because that's already there in the groups of the form C and H, or 2 over m, 4 over m, 6 over m. Diagonal is not defined, so the only additional one that we could pick up by adding inversion is adding inversion to a threefold axis. And that's one we did the other day. Adding inversion to a threefold axis gives us 3 that are up of one-handedness, 3 that are down of opposite-handedness, and the orientation of the triangle is skewed. And that is called 3 bar, but it's just nothing more than a threefold axis with an inversion center sitting on it. Schoenflies notation is C3I. All right, then the only other additions to the single axes are adding the mirror plane in a vertical fashion, passing through the axis. And these we've already seen in 2 dimensions, so we don't have to spend much time on them. There's 2mm, which is C2V, 3m, all the mirror planes result upon adding a single mirror plane to the threefold axis, 4mm and 6mm. These are just 3-dimensional extensions parallel to the axis of the symmetry that we already derived for a plane in space in the 2-dimensional point groups. So we're almost half done. It's easy, isn't it? Any questions at this point? Okay, so the only ones that are really new that we haven't seen already in 2 dimensions are the rotation axis perpendicular to the mirror plane. Okay, that brings us to roughly the middle of the second sheet, and the arrangement of axes 2, 2, 2 represents 3 mutually orthogonal twofold axes. If we add a horizontal mirror plane, that's going to put an inversion center at the point of intersection, because that horizontal reflection is going to be sitting normal to a twofold axis. And then, since the other twofold axes see an inversion center sitting on it, there's a mirror plane perpendicular to those other twofold axes. So adding, again, to go through that again, adding inversion to the point of intersection of the twofold axes creates a mirror plane perpendicular to each of those twofold axes. So it becomes 2 over m, 2 over m, 2 over m. Each of the twofold axes acquires a different sort of mirror plane perpendicular to its orientation. 2 over m, 2 over m, 2 over m, even though I love saying it, is kind of a mouthful. So that's very often abbreviated to just which really is a nice exclamation when you see what a lovely symmetry it is. The pattern shown in the diagram to the left is just the pattern of 2, 2, 2 with the objects reflected up or reflected down, and you get a total of 8. That means that there are 8 operations in the group, and you can add up quickly what they are. They are the 3 operations of rotating by pi, the operation of identity, and then 3 mirror planes because the mirror planes are all distinct, and then the operation of inversion. So there are the 8 operations that are present that generate the 8 objects from a single one. Add a horizontal mirror plane to 3, 2, and you get a threefold axis perpendicular to the threefold axis, so you write that as 3m. And that mirror plane now passes through the horizontal twofold axes, and a twofold axis with a mirror plane passing through it wants another mirror plane 90 degrees away. So a new mirror plane pops up, passing through each of the twofold axes and perpendicular to the horizontal mirror plane. Those mirror planes are in the same direction as the twofold axis. They're not perpendicular to it, and when symmetry elements are parallel to a common direction, you write them out on the same line. So here's a case of a mixed metaphor. One mirror plane that's perpendicular to an axis, the threefold axis, so you write that as 3 over m. The other twofold axes have mirror planes passing through them, so you write that as 2m, and the threefold axes makes all of those 2m symmetries equivalent to one another. Pattern, and this is true for all of these symmetries, the pattern is nothing more than the pattern of the subgroup repeated by the one operation that you've added as an extender. So if you look at the pattern of 3, 2, objects all of the same chirality alternately up and down, add the horizontal mirror plane, the one that is up goes down, the one that's down goes up, and you get a set of 4 around each of the twofold axes. 4, 2, 2 behaves very similarly. The pattern is just the pattern of 4, 2, 2 reflected in a plane. So you have a set of 8 objects, 4 of them up of one, 16 objects, 8 of them up of one chirality. Those are the solid dots, if you will. And then another 2, 4, 6, 8 that are down of opposite chirality. You have a mirror plane that you added as the horizontal mirror plane perpendicular to the 4-fold axis. All of the horizontal 2-fold axes see a mirror plane passing through them, so they've got to have a mirror plane that's 90 degrees away, and those are the vertical mirror planes. And either the point is obvious now or you're not following me at all, so I'll simply say in the left-hand column of the final sheet, 6 to 2 with a horizontal mirror plane goes to 6 over m, 2 over m, 2 over m, called D6H in Schoenflies. I'll leave the cubic ones till last. They're not nearly as bad as they seem, but obviously they have a lot of symmetry all over the place. And we'll want to take a closer look at the patterns. Okay, the next extender is a vertical mirror plane. And we've already got the groups of the form C and V, because they are just extensions in a third dimension of ones that we've seen in 2 dimensions. If we try adding the vertical mirror plane, which is defined as passing through the principal axis of high symmetry and perpendicular to the 2-fold axes, we've already encountered those in every group except 3, 2. 2 over m, 2 over m. 2 over m already has the vertical mirror plane. The same is true of 3 over m, m2. The same is true of 4 over m, 2 over m, 2 over m, and 6 over m, 2 over m, 2 over m. The vertical mirror plane comes in automatically when we add the horizontal mirror plane as the extender. So nothing new there at all. And now we come to one that is interesting. This is the diagonal mirror plane. And I'll do this one slowly and in some detail because it's another example of how we would trip over something if we were not clever enough to think of it. Let me begin by drawing the 3 orthogonal axes of 2, 2, 2. Okay, so we have one object that's up, one object that's down. The 2-fold axis perpendicular to the board will take this one that's down and rotate it to here. Take this one that's up and rotate it to here. So that is the pattern of 2, 2, 2. We can snake a mirror plane in between the 2-fold axes. And a mirror plane passing through the vertical 2-fold axis has to be accompanied by one that's 90 degrees away, half the throw of the axis, which comes from our theorem that says a pi dot sigma vertical has to be equal to a sigma prime that's vertical and pi over 2 away from the first. In terms of the pattern, this second mirror plane that comes up is going to reflect this one across to here. It's going to reflect this one across to here. It's going to take this one and reflect it over to here, and take this one and reflect it to the right as well. So now we've got a total of 8 objects. This one is right-handed. This one is also right-handed because we repeated it by rotation. Then we reflected that pair, so these two are left-handed, reflected across the other diagonal mirror plane. They're back to right-handed again, and these have to be left-handed as well. So there's the pattern. Is there an inversion center in this pattern? The answer is no, because there is no mirror plane that is perpendicular to a 2-fold axis. So this point group has no inversion in it. It's said to be acentric without an inversion center. Do we know how everything is related to everything else? We know how this one is related to this one by twofold rotation. We know how this one is related to this one. That's by reflection across the mirror plane. How is the first one related to this one? How do you get it through 90 degrees and then pop it down and change the chirality? You can't do that in one step. You've got to do just what I said in words. Rotate it 90 degrees. Don't put it down yet. Reflect it down in a horizontal mirror plane. This horizontal mirror plane is not a symmetry element. It's part of the operation that's necessary to get us from this guy over to this guy of opposite chirality. So this is an example of a new type of operation, a two-step operation. This is a 90-degree roto reflection axis. And again, I feel compelled to put the axis in quotation marks because really it's a pair of operations that leaves only a point unmoved. So it's really a point symmetry element. There's another way of describing the same thing, and that would be roto inversion. We could rotate by 90 degrees in the reverse sense, not yet put it down, and invert, and we'd get, again, the relation between, what did I do? Rotate it here, yes, rotate to here, and then invert, and we got that one. So that's another way of defining the relation. So a 90-degree roto reflection is a minus 90-degree roto inversion. So you pays your money, he takes your choice. And what the groundbreakers who went before us did was to take roto inversion as the operation to survive. So here is, if we were not smart enough to invent it, our 4-bar roto inversion axis. So if we hadn't been clever enough, and it would take a pretty clever, devious mind to invent a two-step roto inversion operation, but if we hadn't done it, as soon as we added this sort of extender, a diagonal mirror plane, to a group of the form N22, we would have found that there was a new sort of transformation that could not be described any more simply than to say, take 2 steps to do it. Rotate 90 degrees and then invert. So we have to add the operation of a pi over 2 bar to our basic bag of tricks for generating patterns. The group 3-2 is also a group to which we can add a diagonal mirror plane. And if you do that, again, the bold lines that are mirror planes in that group and the axes that are faint lines are easy to mix up. But if we examine that group with the without the confusing lines, here are the twofold axes. And remember that they are all equivalent to one another by the threefold axis. So this axial group is the group 3-2. If we put down a mirror plane, interleave between the twofold axes, notice that each of those mirror planes is perpendicular to a twofold axis. So we can write this as 2 over m. 2 over m means there's an inversion center at the intersection of the twofold axes with the mirror planes, and a inversion center sitting on a threefold axis makes it a 3-bar axis. So this group is called 3-bar 2 over m. And the pattern is what a twofold axis would do. These would be up, down, right ones. Reflect those, and you get an up, down pair of left ones. Reflect again, you get an up, down pair of right-handed ones. Reflect yet again, and you get an up, down pair of left-handed ones. Reflect still once more, and you get a down, up pair of right-handed ones. One more time, up, down, left-handed ones. So you get a total of 2, 4, 6, 8, 10, 12 points. So this is 3-bar 2 over m. In Schoenflies notation D3, that's the symbol 332, with a diagonal mirror plane added, and you indicate that by a D in the subscript. Okay, I think that's probably a point where you're more than ready for a break. We've got very few yet to do. One surprise is that if you add diagonal mirror planes to 422 and 622, you get perfectly lovely exquisite groups, but they're not crystallographic. So we don't include them in our list. But we'll discuss them when we come back, and then take a look also at the cubic symmetries. Impossible to draw, but really not all that difficult to understand. So let's stop at this point, take a stretch. People are stretching already, they need it. And we'll resume in 10 minutes' time.